Hello friends, we are at step 3 and we have covered part 1 of step 3, that is IO ports, part 2 serial ports, part 3 interrupts, and now it is the turn of MP3 device. So let us study MP3 device. We already had a brief introduction to MP3 device in our earlier lectures. Now let us have a closer look at this device. You should see the CPU communicates with this MP3 device, that is MP3 module, on serial bus. As you can see, the TXD, the transmit, and RXD, the receive, these are the two pins with which CPU is connected to the MP3 module. There is no other connection. Then MP3 module itself contains a SD card, because there is a slot for it. So there is an SD card from which it reads audio files, and then it reads files and sends the audio output on this device, the earphones. This is the basic structure. So remember, CPU card will communicate with MP3 module only on TSD and RXD. So whatever functions it wants to achieve, and what are the functions it wants to achieve? They are next, previous, accept, and up, which is related to navigation. So with the help of these keys, the user can select a desired file. But to select that file, it has to send a certain string on TXT, right? It can also control volume. Increase the volume, that is volume plus, decrease the volume, that is volume minus. To cause this also, it has to send data on the transmit line to the MP3 module. If it wants to pause or resume, that information will also have to go on the TXT bus on to the MP3 module. So these keys are for the user to select the function. These two pins, they are meant for communication with the module. So whatever function user wants to implement, that is implemented by sending an appropriate string on TXT line. That's how it is. We can see it physically. Here we have the microcontroller, and this is the device, the MP3 module. Physically, the device looks like this. It has got VCC, two ground lines, RXTX, that is what we are going to use, pin number 2 and 3. This pin number 1 is 2 and 3. So here we have 2 and 3 RX and TX. We connect the earphones to DAC right and DAC left. So this is pin number 4 and 5. DAC right is 4 and DAC left is 5. So we are using 1, 2, 3, 4, 5 pins, then ground 6 and this is ground 7. We are not using the USB implementation. Okay, so what we are going to use is DAC R, DAC C for outputs, that is for the earphones. We are not using speaker 1, speaker 2 for output. Here we can connect a speaker which is having less than 3 watts of wattage. This is how it is. Now let us take a look at the MP3 module. If you remember, I had asked you to download the data sheet of this device. So I will go to that data sheet. This is the device FN M16P embedded MP3 audio module. This is the data sheet of this module. You will get it, if you have not already got it, you will get it at this link. This is manufactured by Flyrron Tech, FLYRONTECH.com. If you go there and look for this device, then you will get this complete data sheet. Let us have a further look at this manual. Here you will see the main features. This particular device supports MP3 as well as WAV decoding. We are interested in MP3. Then you can see here supports maximum 32 GB micro SD card and 32 GB USB flash drive. As I just mentioned, we are not going to use the USB flash drive. We are using the micro SD card. And then it supports 3000 audio files under the root directory. We are going to use the root directory, and of course we are not going to need 300 audio files, but if you wish you can, and you can go up to 3000 audio files. There is another way of arranging the files. You can arrange these files in 99 distinct folders, and each folder can store 255 audio files. So this is another way, but we are going to use this method of storing files, audio files in the root directory itself, and we can go up to 3000 audio files. Then we have the working voltage 3.3 to 5 volts, typically 4.2 volts, and the current it draws is less than 15 milliamperes, provided we don't use USB flash drive. So if you use SD card, then the current consumption is much less, which is less than 15 milliamperes. As I have mentioned earlier, whatever function I want to perform, that is specifying the track, as you can see in the commands of interest I have mentioned here, whether we want to specify the track, which of course the user is going to want, and for that navigation facility is given with the help of keys that I have mentioned earlier. So user may want to specify the track, increase volume, decrease volume, play, pause, audio amplifier setting, and telling it that I want MP3 format and not the WVA format. So like that, we need these functions. These are the function numbers. Now, and all this is stated in hex. When I say 10, it is not 10, it is actually 16. 12 is not 12, it is actually 18, like that. So we have to send a string. What is the way and format of this? The format is, it has 10 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The start byte is always 7E. First byte is start byte, it is 7E. Second byte is version, and version has always over the time remained FF. So this also remains fixed, FF. Number of bytes is 6. This also is fixed, and these things change. Command, as we have seen the commands in number 3, we have seen commands are can be 3, 4, 5, and so on. So we have to give command 1 byte. Then whether I want a feedback from MP3 audio module or not. If I want it, then I will write here 1. If I don't want it, I will write here 0. So this byte will be 0. Remember, it is a byte, not a bit. So it will be 00 in hex. Then some of the commands, like the specify track, this command will require parameter. What is that parameter? The address. So address has to be 16-bit, and we will be giving MSB here, most significant byte here, followed by the least significant byte. After doing this, we'll have to send checksum. Checksum is also 16 bits, that is 2 bytes. MSB of checksum and then LSB of checksum. and the end byte is always EF. So there are 4 bytes which are fixed, which you cannot change, and the remaining locations you have things that vary depending upon the requirement. So the start byte is always 7E, version number is always FF, number of bytes is always 6, and end byte is always EF. This is the way it goes. Now let us take one example. One example is given here. I want to access address 1000. That is the file number 1000. Example is a command for playing the file number 1000. So we first convert this 1000 into hex, so it becomes 03E8. So its MSB is 03 and LSB is E8. So what we will do first 7E, these three are fixed, 7E FF06. Then the command is I want to play the file. So play the file means specify the track. So I have to specify the track. So command is 03. And feedback, I don't want feedback, for example. So I write here 00. Then I give the parameters. The parameters for this command is address, and just as we have seen, address is 1000, expressed in hex it is 03E8. So it is 03E8. Then there is checksum, and finally EF. So we have to calculate the checksum. That is, the microcontroller will have to calculate the checksum and feed it here and here, the MSB here and LSB here. How will you get the checksum? I have taken another example in which I want to read or play 10th file. So command is 03. The file is 000A. A means 10. So 00 is the upper byte and 0 is the lower byte. So I will write 000A followed by MSB of checksum and LSB of checksum, and EF is standard, it never changes. This is the end byte. So the question is now, in this particular example, how do I calculate the checksum? Checksum is obtained by taking 2's complement of the sum of 6 bytes of serial data starting from second byte. Second byte is this. The first byte is 7E, second is FF. So FF 06, 03, 00, 000A. These are the 6 bytes. 1, 2, 3, 4, 5, 6. So these are the 6 bytes. I shown it here. FF, then 06, then 03, then 00, then 00, then 08. I add them up. They're all hex numbers. I add all these numbers. The sum is in hex. The sum is 0112. I take its 2's complement. I hope you remember how to take 2's complement. You take 1's complement and add 1 to it. So the result is FEEE. So this is how I got checksum FEEE. So the string contains FE as the MSB of checksum. Checksum MSB FE, and checksum LSB in this case is EE. If you try, you can use these 6 bytes FF 0603 0003 E8. If you make checksum of this, that is add all these numbers and takes 2's complement, you will get FE0D. So this is how we have to send data in a serial format, and the number of bytes that we send is 10. That is one thing. Second thing is we have to give data at a rate of 9600 baud, 9600 baud. Let us have another look at the data sheet. It says the data we send, serial commands, supports asynchronous serial communication mode. That is what we are doing, via which accept serial commands sent by PC or microcontroller. So what are the constants for this? Communication standard 9600 bits per second, that is 9600 baud, 9600 bauds. Number of start bits is 1, flow control is none. What is written here is really not correct. Data bits, it is not data bits 1, it is the start bit, it is only one start bit. Data bits, there are 8 bits, and so there is an error in this. So let me mention that the baud rate is 9600, then data width is 8 bits, that is it contains 8 bits of data each byte. Then there is one start bit, one stop bit, no parity, and no flow control. This is how we have designed the example that you have seen just before we saw interrupts, right? You remember that. So, as we have already seen, the versions, we had to give the start bit, version number, command, feedback, parameter, MSB, parameter, LSB, checksum, MSB, checksum, LSB, and $0. So we have seen the values of this, all this. So if you want, you can refer to this, but remember that this is erroneous. This is not correct. Communication standard is okay. It is not standard. The speed of communication is this. Okay. So this is the what the manual says about data, and we have decided to use 9600 baud, one start bit, one stop bit, no parity bit, and data is 8-bit data, no flow control. Now we know how to send commands. These are the commands. If I want to say, if I want to specify track, then what I will do? I will only change this value here. If I, that is, write the command 3, and I don't want feedback, so 00, and then this will be the address, and then the checksum. So if I want to increase the volume, then instead of 03, I will write 04, and then I specify here the volume I want to maintain. Decrease the volume, so I will change the volume here. If I want to play or pause, so if I want to pause, then I should send 0E here. Instead of 03, it becomes 0E, and nothing here, it is 0 zeros. If I want to play, then 0D. So if play means I resume. Then here I will write 0D instead of 03, and there is no parameter to be given. Play and pause, like that. So if I want to specify that yes, I want MP3 format, not WVA format, then I will give a command 12. So instead of this 03, I will give 12. And it does not have any parameters. But every time you have to calculate this, the controller will have to calculate if the checksum, and MSB will be written here, LSB will be written here. So whether this command contains parameters or not, you will have to give appropriate values. If there are no parameters, then fill 0, 0, 0, 0. If you don't want feedback, then write 0 here. If you want feedback, then write 0, 1 here. And checksum has to be calculated and inserted, and finally this. So every time you send data, it will be 10 bytes of data. Speed 9600 bauds, start bit 1, stop bit 1, no parity, data is 8-bit data, each byte that you send, and there is no flow control. The next important thing is data returned from the module, and this information is available, details are available at page 8, and when I give numbers like page 8 or page 5 here, or page 6 here, or page 4 here, It refers to the page numbers of the MP3 module datasheet. Okay, so when we switch on the whole instrument, that is the CPU and the MP3 module, MP3 module will take some time to settle down, and when it settles down, then only we should give it any command, not until then, because it will either misinterpret or it will not understand what all this is about, and therefore you must wait until it says, yes, I am ready to receive. That ready signal comes in the form of, as you can see, data returned from the module. It comes in the form of this string. This 10 bytes will come from the MP3 module to the microcontroller on the serial port, and if you see this string of data, then only you know that yes, now I am ready to start communication. Not until then. So if you go to page 8, we go to page 8, page 4, page 8, enter. Returned data from module. So when it powers up, it sends, if all is well, then it sends this or this or this or this string. When it sends this string, what does it mean? It means that USB flash is active, connected and active. It cannot be active unless it is connected, of course. And if it sends this string, then it would mean that SD card is active. If it sends this, then PC online, that connection is active. And if it sends this, it would mean that both USB flash is active and SD card is also active. So you can choose one of the two. Now, in this string, you will notice that it has 10 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The string that we had sent also had 10 bytes, and this also has 10 bytes. And the sequence of data is start 7E, version FF, number of bytes 06, same as when we sent it from the microcontroller, and last is always EF. So these 4, 1, 2, 3, and this 4, they remain the same. Now this is 3F, so it is giving a feedback 3F. So if it is 3F, then excellent. Then we know that it is the SD card, 3F here and 02 here. 3F is I am responding, yes, everything is fine. And what is the fine thing? Is the SD card is active. So it is 02. So if I get this string, then I know that the SD card is active, and now I can send the commands. Now here it is given XXXX. So what you have to do is, when you receive this data, you will be actually receiving XX and XX, real values of X. Let us see that. We have done it on that. The data that has been returned from the module is 7EFF06 3F. 3F is, these things is healthy. And what is healthy? It is 02, which stands for the SD card. So if SD card is okay, then this will be 02 here. And this FE and BA, this is the checksum upper byte and this checksum lower byte. In the manual, it was written XXXX. So it could have been written as FEBA. Before I end today, let me tell you why do you need checksum. Checksum is meant for error detection. When you send this data, we know that this figure FE and BA or whatever comes at checksum is a fixed number. It depends on entirely on what is the content of 1, 2, 3, 4, 5 and 6 bytes. Based on this, it adds them up together and takes 2's complement and writes it here. So when we receive this data sent by the module, the microcontroller will calculate the checksum. If it finds that checksum is FEBA, then it knows that there is no error in data transmission. This is the purpose of checksum. It is for error detection. So friends, at this point I stop, and next time we will take a look at product operation flowcharts, and the first item in this is data file organization. We must organize the data in such a way that user can comfortably navigate and very fast, very efficiently reaches the point or the file which it wants to hear. So it has to be carefully designed. This is what we are going to see in our next lecture. So thank you friends. If you have any difficulty, you can contact me, or you may even go through the lectures again. Until then, thank you.